Hi, everyone. Welcome to Lab 3. You can download the lab in B courses. Before we start everything, you can set up your poll everywhere, and I'll go through the survey last time. So the pacing last time improved, I think, quite a lot. And then the poll everywhere participation survey is, the usefulness is near neutral to beneficial, and the amount is a little bit too much. So I have dialed down this time. The amount of independent coding is how the usefulness is neutral or useful, and the amount is a little bit too less. So I'll give more independent coding time this time. The amount of lecturing time or just me talking is close to optimal or a little bit too much because we had NumPy last week. The amount of live coding instruction is a little bit under, I would say. So I will increase a little bit of the live coding this time. The usefulness of NumPy and matplotlib are neutral or beneficial to everyone. And the responses I got from everyone, we will continue to do the polls and examples with live coding and give everyone the time for independent work. And we'll also have TA going around for one-on-one help. And the feedback is also helpful. So I will keep giving out the feedback surveys. The things that were not so helpful was reading a lot of descriptions, making too many polls, and too much lecturing on basic NumPy and the lack of connection with lecture topics. Hard to see the screen. So I have increased the font size. Hopefully you can see the screen. And there are a lot of typos in the lab. So the typos, I was the only person who made this lab. So sorry if I have typos. Please let me know if you have seen more typos. Usually, if it's graded, I will give out extra credits, but this is based on participation, so you'll get my compliment. Can have more discussion about the common mistakes made. I'll discuss more during the live coding. And for lecturing, we won't have more lectures because all the basics are covered, and hopefully we are on the same page. And the description part, I think it's more of a, getting everyone on the same page thing. And there's conflicting feedback on the amount of practice problem and live coding I should give. Some suggest that I should just give everyone the independent time and not doing any practice on the screen. But an overwhelming number of students suggest I give more examples on the screen live coding and reflected by this questions response. So what I will change is to keep the current teaching format to have guided examples with live coding, and you'll have opportunity to code. And I've decreased the number of poll everywhere polls, so you can focus more on the coding. And feel free to work independently or work in groups. And the notebook is written in a way that even without me, you can understand it. And it's more of an added benefit. So, but I still have to teach the content up here. So you're more than welcome to do all of those independently. Any questions? Okay. So do you guys have everything set up here? Let's see. Okay. Hopefully everyone has this set up. I think we have more than 14 students here. Okay. As you continue to set up your poll everywhere, I will go into the lab for today. So the lab today will cover the implementation of numerical differentiation method. So we already know how to take derivatives and differentiate using analytic expressions, but here we're learning it how to do it on computers. And we will understand what are the errors associated with the method and the order of those methods using big O notations. So before we begin, we just import the packages, NumPy, and then the secret sauce for data visualization. So let's review a little bit of Calculus 1. So in Calculus 1, we learned that the derivative is defined using a limit so that we can define it as like a slope. So we have the y value at one point minus the y value of another point divided by the interval between those points. And the critical component here is to take the limit to 0, and the geometric meaning is the slope of the tangent line. But on a computer, we don't really have that continuous thing. We are having a discrete intervals. So what we can do is to just approximate that and not taking the delta x to limit to 0. We'll take it to a very small number. And the method that's using finite or discrete points to approximate the derivative is called finite difference method. Okay. Let's see the poll. How confident are you in the definition of derivatives? Hopefully pretty confident. Okay, that's good. That's good. And I have put some review up here, so hopefully you can get more exposure and connection with this lab, these definitions. The first method I will introduce is called the forward difference approximation or method. It's basically the same formula as the definition of derivative, but we're not taking the limit as delta x goes to 0. We're just taking it to a very small difference. And we can show this with an interactive demo, where here I'll introduce the components individually. So we have an analytic function exponent of 0.2x here. And I want to take the derivative. And we already know the analytic derivative at a specific point x equals to c. And c is defined as 0.14. So I can show that point here. So to get that derivative, usually what we do is to take the tangent line. And here's a tangent line. But the tangent line has to be very, very close so that it's just at one point. But here I've shown that a secant line where you connect these with 2 points. So when the h goes smaller, the slope approaches the derivative at that point. But numerically, we can calculate the derivative using such approximation to look at the slope of the secant line instead of the tangent line. So that's the theory behind forward difference method. And to code that up, we can first try to find the derivative at one point. So find the numerical derivative of the function. So we can first define the function as f is equal to the lambda function of x of sine of x. And that is a function. At point x equals to 0, so let's define the x point is equal to 0. Using a former difference method using a step size of these step size. So the step size we can write as dx, and it's a list of values. And then this is 1.1.01. So this is 10 to the 0, 10 to the -1, -2, -3. So we can say 10 raised to the power of numpy a range from 0 to -1, -2, -3. So -3 in a -1. But note that we just do that. Okay, it gives an error saying that the integer cannot have power. So what we need to do is to write that as a float. So 10.0 raised to these power. And note that we're ending but not including a -3. So what we should do is to make it -4. So now we get all 3 step sizes, all 4 step sizes. And then we want to define the forward difference algorithm. And to define that, we can write a function. So def forward difference. What should we take in? We should take in the original function, some delta x, and I think that should be it. And then we return some value. And the algorithm is shown here. So what should we do? We should get f. Oh, we also need the point at which we're defining the derivative. So we have f evaluated at x plus delta x. So x plus delta x minus f of x and collectively divided by dx. And this is the forward difference at a point. So we return that. Okay, need a colon. And then we can run this forward difference of our own function f with an x point, which is 0, with a dx. But the dx is in a list, so we need to use a for loop. So for dx in the dx list, we can print the forward difference solution. Okay, any questions? Yes. Yes, so the numpy function arrange is when you have a left bound and a right bound known, then you need to use a range. And the left bound is including the left bound. But the right bound is stop there, but not including. For example, if I have 0 to 10, and then the third argument is the step size. Let's say the step size is 0.1. So what it tells it to do is to start at 0 in a step size of positive 0.1, go to, but not including 10. So if we run this, is starting at 0 in a step size of 0.1, up to, but not including 10. Great question, okay? And that's for this practice problem. So we already know the analytic derivative, which is cosine of x, and evaluated at 0 is 1. So the smallest step size here gives the most accurate solution compared to a larger step size. Now here, in this problem, we define the derivative at a point. But what should we do if we want to find the derivative for a function? So this is what this example is about. So we can similarly copy and paste what we had already. So the forward difference algorithm is still the same, but now, and the function is still the same. So I can copy the function. But what's different is that now we're not just evaluating at one x point, we're evaluating a range. So the x range, so x list is from -2 pi to 2 pi. So MP Lin space, because we already know the left and right bound. So -2 times MP dot pi to 2 times pi. Let's say using a step size. So the step size is already defined. So what instead we should use is not Lin space if we already know a step size. So we should use a range. So here we're arranging from this to here using a step size of 0.01. So the dx is 0.01. And put a dx here as a variable. Okay, but note that if we print out the x list, you'll find that the last element is not exactly 2 pi. The reason is that it's up to, but not including. So what we usually do if we know a step size and we want to include the right boundary, we can just plus a step size here. So now it's at 2 pi. Okay, now we have a list here. So now we want to find the forward difference of that function. So forward difference of the function defined with the x list with the value of dx. So now this should have 1,000 points. So let's look at the length. The length is 1,200. It should be consistent with our x list. Yeah, they have the same length. And now we can plot this. So let's see if there's more instruction. Plot the numerical derivative with the analytic derivative. So to plot it, we can have figure axes is equal to plt.subplots, the standard command. And then within the axes, we can plot the x list and the derivative. Where's our derivative? I think I deleted that. Okay, forward difference f x list dx. Okay, so this is y forward. Okay, and we can plot it here. So this is the derivative. And we can label it. So set x label as x. Oh, it's a string of x. And set the y label as f prime of x. And because we already have the prime outside, so we need a backslash to escape the character. Okay, and we also want to plot the analytic solution. So analytic solution is just what's the derivative of sine? It's cosine. So we just plot pi cosine of x list. And it's basically the same. So our algorithm forward difference method recapitulates the analytic expression pretty closely, at least when we look at this graph. Any questions? Okay, and we also want to plot the other things with these commands, which I think you guys can do, which we went over last time. Okay, now it's your turn to implement these algorithms with backward difference method with these formula as well as the central difference method. please let us know if you have questions and we'll come around to help you. So this is a B course. Yes. B course finals lab.
In this A range, how does -1 exactly?
So it just minuses one from the zero and then 0 minus 1. And then -1 except until it reaches -2 and -4. And it doesn't.
Okay, gotcha. Thank you.
Yes. Last one. That's the same one. Last week's Monday. Monday, Tuesday is the same. Each week we have the same.
You're saying that any closed function. Yeah, so this way, like, for example, you put 4 weeks, you don't have to like write it out. All the, it's like, what is it? Saying that, like, you're defining X equal yeah, so you can change it. You run the X equals, or run the X equal sign. You can go by. Yeah, just convention. Like maybe you add the dice, but there's no reason you can't like tell you know what I mean? Like just leave it when you like.
Yeah. So all the I made another typo again. Sorry. So for start this problem for basic central. Before we put it on So we need to stop it. First comment is restart. I think it's due to you might have some more qualified. The data hub doesn't sorry.
Oh.
So I feel like it could be more helpful also. for differential. So because they have like still connected to stuff. Like study. Or there's a different way to study. Like for this example.
So this is like the standard syntax for defining a function. And this function contains four different algorithms.
What is X?
What's this?
Because you put that X. So are they?
So you can define it on your own.
Oh.
I just use one. So dx represents delta x. You can also write a delta underscore x. You just need to make that consistent.
That's kind of confusing. I don't think like for this one. Lambda X, what's lambda X?
Oh, so that's basically just a way to define, you're just saying that f is gonna be a symbolic function of x. So the same way we write f parentheses x right on paper, that's the same thing you're doing for computers. So if you scroll down, it's basically what this line is right here. So it's just the way you're writing it, I thought, like lambda is gonna be like what
Oh
you're
my
comparing, and then sign of x is your thing, but you have to specify that this x is the same as that. So you could change them both. to
Or
y,
multiply
it's
it
the
by
same thing.
1 over. Right.
Thank you.
Oh, I see.
There we go. Number 4. Good. Hold on, let me change. I'll just do it.
Having foundation for the what these are the final comments. You can look at it. Have you done lab one?
Yes.
No,
I think just did the first 5 minutes later.
Also,
Oh, you did a ring. Oh, the last one, the one that would be so. Yeah, but I didn't ranks on that.
well, no, it's based on that.
don't know which one is the one that is there.
Not only one, the other. Lab two is all the. Lab three is now.
Tomorrow is not.
No, tomorrow is not. Three is the assignment.
Oh,
These are the sections.
Oh, this is. Tomorrow is.
Tomorrow
Yeah,
is.
this thing.
Yeah.
Lab is.
Both is lab three.
Yeah. But it is a different section.
Yes, there's different students.
Yeah, this one. Yeah. And that's one. So it's. Maybe then Monday. When.
That would be the same for the second. Okay, anyone need more time on the first four practice problems? Okay. What?
Is there what it calls the secant function of that?
No, you have to do the old fashioned 1 divided by cosine.
Well, that should.
Okay, I will briefly go over the practice problems and then we'll move forward with the other content. So what we need to do is to copy and paste all the code above and then only change the core parts And the core parts are the functions and the method. So we have the forward difference method, the functions list, and then the printing statement. Okay. And now we're using backward difference instead. Backward difference, and what is backward difference defined as? It's defined as f of x. So instead we have f of x minus x minus dx. Okay, like in this equation. And then the function we defined as cosine function, and then the step size is still the same. And then we can print it. Now changing it to backward difference. And now we have our answer. And the analytic result is NP sine of 0, should be 0. So as you decrease the step size, the accuracy increases. What? So this is the original function, and this is the derivative.
Okay, I got you.
So these two should be very similar. And to plot the whole function, which is the next problem. So here I made a typo. We should use the backward difference instead. So here, what we should do is to use a step size and then change the range. So instead, we should have a x is equal to NP, a range from 2 minus 2 pi to 2 pi in a step size of 0.01. And then we'll add that step size here. So let's define that dx as step size. And then we don't need the dx list. Then we can use the backward difference here. But instead of 1 point, we're plotting it against a range. And then for plotting, we can use fig x is equal to subplots, and then f x, and then that is defined as y of backward. X plot. And this should be the derivative, which is negative sign. You can also check that by plotting negative sign of x, and it should be the same. Similar method goes with central difference. So we copy this and paste it here. And here we're using tangent function. And then the central difference is defined as f of x plus dx minus f x minus dx divided by 2 times dx. And then the function name is central difference. And then we're using at 0.0 and then the same list. Okay. Oh, tax. Tangent. Okay. And then we know the derivative of tangent is secant square of x, which is 1 divided by cosine. Cosine of 0 should be 1. 1 divided by 1 is 1. So that as the step size decreases, the accuracy increases. And again, we can copy the backward difference code for the forward difference, central difference. So here I made 2 typos. The function should be tangent of x and the method should be central difference. So central difference x plus dx. And here it should be tangent function. If we plot it, it should be like this. The reason is because we have going to infinity, so we need to constrain the axis. So set the y limit as 0 to 10. So now this looks better. Oh, and the step size is 0.001. Okay. And then we can plot the analytic expression, which is 1 divided by cosine square. which is the same. Any question? Yes. So both can accomplish the same thing, but the input is different. So a range I have showed before, which is the left bound, say -2, and the right bound, say 2. And then the step size, we can define it as +1. So this gives this. We can also do is to, since we already know the left and right boundary, NP Lin space, this time it's input the left boundary, right boundary, and this time it includes the right boundary. And then the third argument is the number of points. So it will equally space the points between them. So here we have 4 points, so it accomplishes the same thing. It depends on what information you know to choose in between these two. But both can achieve the same thing. Okay. Any questions on the 3 numerical methods? So we use these 3 methods to look at the derivative of analytic functions, but in reality, we usually do not have analytic functions. Instead, we usually have data points. So in this case, we first look at data that's sampled along a constant sampling interval. So the delta x is the same for every data. So instead of using this kind of analytic f function, instead we're using data y. And the forward difference can be defined as the data point I plus 1 minus the data point of I divided by the constant interval. And we can go through an example, and this time the example has chemical engineering meaning. So it's a fouling ball viscometer. So in transport processes, you will learn how to measure the viscosity of liquids. And one of the methods is to use a fouling ball viscometer. And you can click on this video and to see what the instruments is actually like. It's like this type of stuff. You fill the liquid of interest inside these columns, and then you put a very small ball of known properties like mass, radius, etc. And you put the ball inside the liquid. And you will observe the ball falling at a specific velocity. Initially, the velocity will increase, but to a certain point, it will reach its terminal velocity, at which its velocity does not vary. And it will constantly go until it hits the bottom. And to measure the viscosity, there are theories to connect the terminal velocity with viscosity. And therefore, measuring the velocity in those cases is very important in determining the viscosity. And here in this problem, we're looking at how we can take camera pictures to look at the time and the position, and taking the derivative of the position to get the velocity. And then with the velocity data, we can calculate the viscosity. Okay, so here we have measurement of the terminal velocity or the position. Here we have the measurement of position from camera with the equidistant spacing of time from 0 to 3 seconds with a step size of 0.1. So we have already a given data set of the position. And we're told that the time is ranging from 0 to 3 with a step of 0.1. So we should use, since we're given a step, we should use NP arrange because we can input a step. So the left bound is 2, right bound is 3, step size, let's say it's called dt, is 0.1 second. If you print this, you'll see that it does not include 3. It's because it's ending at, but not including 3. So what we can do is to plus a dt here, and then it will include 3. Okay, so now we have the position and the time. Plot the position with respect to time. So what we can do, fig x. By now you should be able to like know how to write these. So x, t, and position. So this is the position curve. And then it asks us to use point markers and do not connect the markers. So the syntax for a point marker is O, and it will give you these type of points. You can also try things out like a 0. Don't think 0 works. So point gives you a smaller point, and the X gives you like cross marks. And then let's label these plots. Always label your plots when you're doing like lab reports. So the X is time, T, and what are the units? The unit is seconds. And let's label Y. Y is the position. And the position, the unit is centimeters. Okay. It should be set X label and set Y label when you're using axes. Okay, so this should be like a sample plot if you're submitting your homework or lab. Should be well labeled with the tick marks as well. Okay, same thing. Calculate the velocity of the following ball over time and plot the velocity with respect to time. And when we recall calculus, what is velocity? Velocity is the derivative of position. So what we can do here is to use, well, it didn't specify which method. So let's use forward difference method since we're in the forward difference section. So the method here, we cannot use the same function as before because we don't have the same analytic functions. So what do we do? Instead, what we have is the data y and the increment dt. And how do we do that? So the formula, let's copy and paste that here. The formula is like this. Oh, wrong formula. Okay. That is for continuous. For discrete one, it should be like this. So you're using the y at the ith point minus the data at the ith point, I plus 1 minus I, and then divided by delta x. So let's write that in. So y should be a list indexed at I plus 1 minus y of I divided by dx, or in this case, it's dt, same thing. But how do we define I? So in this case, we need to use a for loop for I in the range that is the same as the length of the data. We loop this through. And we want to store this data. So let's create a list. So let's say dy dx list is equal to empty list. And then we can append this list with the result. And we will return this list. And if you run this, you'll see that it will give you an error, actually. So position dt. So it will give an index error. And why is that? It's because you're ranging it from for the length of the whole data. But the dy dx is actually, you can't get the same as the length. The reason is that if you have some interval, you have a data at different intervals. Say I have 3 data points here. We have 3 data points. And you use the forward difference method. It uses this range to calculate the derivative at this point. And then it uses this range to calculate the derivative at this point. So the data originally had 3 points, but the derivative dy dx only has 2 points because you only have 2 intervals. So if we have n points for the data, we will get n minus 1 point for the derivative, for numerical derivatives. And in this case, we're assigning the interval that's later than the point to that point as the derivative. But what we should do in this case is to modify the for loop so that it ends at length minus 1. And now we can get our forward difference. And we can also make it an array. Okay, and then we have the velocity over time. So we can plot this fig x is equal to plt dot subplots, and then plx plot the t and the position. And note that the velocity. So this is the velocity from forward difference. And we want to plot the velocity. And note that you also want to adjust the length of the t because the length of the velocity is t minus 1. So we need to index t from the start to the end. So this means that we're getting 1 less point. So the difference between t and t to the last point is that we don't have the last 3 here. We plot this, this is the velocity profile. Use point markers to connect with the solid line. And this should be O dash. So you see that the velocity, so let's label this plot first. Set x label should be x, y label should be b of t, should be t, because it's time. So the velocity, we see that initially the velocity is small, but to a certain point, the velocity is almost constant. And why is it going up and down? It's because of the measurement error. But we can see that the velocity is almost constant. So it has reached the terminal velocity at around 0.2 seconds. Okay, same plot. So the terminal velocity is defined as the near constant final velocity of the ball when it's freely moving in the liquid. So when did the ball reach its terminal velocity? So when it's almost constant, it's around these points, and then it's around 0, 1, 2, the second point. And the second point corresponds to 0.2 seconds. Estimate the terminal velocity. Then we want to take all these points and take the average of them. So what we can do is to look at the velocity forward and say, okay, we don't want the first 2 points because it's initially starting up. So we can index it starting from 2. And we don't want the final 4 points because it has already reached its bottom. So when it's at the bottom, we don't count their velocity too. So we should index to -4. So we discard the final 4 points. And we take the average of them, and the syntax for average is dot mean. So that's the mean. So the mean velocity, terminal velocity should be 4.11 centimeters per second. You can also calculate their standard deviation by putting in STD, standing for standard deviation. And the standard deviation is around 0.3. And this is coming from measurement error. Any questions? Okay, and you can try the same problem, but with backward and central difference. Yeah.
Backward, would we subtract I still, or would we add 1 to I? If that makes any sense.
So for backward, we're counting. So I minus 1 minus I. Right. So I don't know if you can see that. So we have different intervals.
Yep.
Let me come to your section.
Okay.
Forward difference, we're looking at using this interval to calculate this.
Yep.
And for backward, what we're looking at is to use I minus 1. For example, here is I, there is I minus 1. We're using this interval to give it to P.
Yep.
We're using this to give it to P. So the time that you should index should be from 1 to the end. You don't have a time because you're losing one data point.
So the length
to be arranged from starting at 1 and ending at final position.
Okay.
Reason is that the interval will be so for your operations.
If you're wondering, like, thinking this one, if you want to submit, what can I do? Like, this is this problem that work out. How can I?
What do you mean submit?
Like, maybe like do this one.
Oh, you wanna use this?
Yeah.
You can just copy and paste it.
Oh, copy and paste it
Into just whatever,
Okay.
whatever your Jupyter notebook is for that. Like whatever you're coding on, just copy and paste this in the beginning, basically. Yeah, that should work, because this is just like nice plots, and then this is just packages. So
Okay.
there's no like.
That's cool.
Yeah.
No, okay, so this is the only one. The other ones were just to see what the plot looks like. This is my code for that.
Wait, what's the this one? They're like different.
Yeah, that's right.
It's just.
Or section was it fixed?
No, I got it.
It was what if we need a set make the matrices equal integers and so forth. Because one is the
Understand. It's at this point we redefine these we cut off.
Yes.
And would this be the correct way to do that?
Yes.
Okay. Okay. This setup, if I put one,
Starting in one.
okay, so it's not like those, it's inclusive then? Okay. Okay, 'cause that was my big question, but I guess that answers that. Thank you.
Yes, when you scroll down, this is a long notebook, so you need to scroll down. Can use the STD function. Is it? Yep.
Yeah.
For problem five.
What is that about? Because you guys can do it. And then what's your
And you have extra time. Yeah. Yeah.
Oh, I don't understand what you're talking about. For central, right? It's looking at one behind. Yeah. If you start getting X zero, it can be like.
Shit, dude, I don't know, it's not to do with it.
It's not like,
He's like, it's for, like that, which one? I didn't know what I was doing.
Wait,
No.
Like you copy things from the and then
They're not great. I don't think so. No, they're full. Really? Oh my God.
well, I definitely no, this way.
I got different,
This, no,
really?
you can have some number in the beginning, it's including that. To be.
Return all these four, or print all these four statements in one code.
Yeah.
I mean, you can print
Oh, yeah, I
all
know.
on the list, or you can just, like, you can just copy the term and then just
But I mean, aren't you better when?
Because if I just do it like this, all I get is the last one.
I guess.
You can try and do like print of all of them in some sort of
Okay.
like a list.
Okay.
Okay, I will demonstrate how to do the practice problem. Before we go, let's look at some common issues. So when we look at these numerical algorithms, we're again losing the points. And the reason is because we have these discrete data points, but we have one minus that number of intervals. And for different methods, we need to exclude different t, for example, in your examples. So for forward method is I plus 1. So y at I plus 1 minus y at I. So that means we're using the first interval assigning to the first point, the second interval assigned to the second point, and the ending point. Do we have I plus 1? We don't. So we exclude the last point for forward difference. And for backward difference, it's the reverse. The backward difference is I minus 1 minus y of I. So the first point, do we have the I minus 1? We don't. So the first point is being excluded from the algorithm. And the second point, we have an I minus 1. And this interval is assigned to the second point. So first interval assigned to the second point, and then the third point is I minus 1. So the second interval is assigned to the third point. So for backward difference, we also lose a point, but instead we lose the first point. For central difference is y I plus 1 minus y of I minus 1. If we look at the initial point, does it have I minus 1? No, so the first one is being excluded. The second point, it has a minus 1 and it has a plus 1. So this whole interval is assigned to the middle point, and therefore the central difference. For the ending point, does it have an I plus 1? It doesn't, so that point has been excluded. So the central difference basically excludes the two endpoints. So when you're plotting your figure, the t that you want to plot to, you need to use list slicing to change the interval for the t. So keeping that in mind, let's do the practice problem. So we are given the position and we know the dx. So the dx is constant, 0.1 seconds. And then the time is from t is equal to np arrange, because we already know the step size. So from 0 to 3 plus b, say dt. Okay. We have these points. And then we can plot them. We already plotted them last time. We can use the backward difference. So define the backward difference, but this time for data points. So what we already know is the data point, let's say y, and the interval dt or dx. And the algorithm says that it's y of I minus y of I minus 1. And then the whole thing divided by dx. And this is our dy dx. And we need to define these I, so we need the for loop. So for I in range, and we need to be careful about what this range is, because backward difference, we're using I minus 1, so we're losing the first point. So we need to range it from starting from the first point to the ending of this array. So the length of y. So this is different from the forward method. Here is different. And then we define this dy dx, we want to store it. And to store it, we can create a list. So empty list, and then here can append the list with the value. And then finally, we will return the list. Okay, let's try that out. Backward difference of y, which is the position, and then dx, which is dt. Okay, so it returns a list. Let's make it a NumPy array. So now it returns like a NumPy array with backward difference. Let's assign it as y of backward. Okay, and similar things we can do with central difference. I just copied the code and change it to central difference. And this time the algorithm is y of I plus 1 minus y of I minus 1 divided by, importantly, 2 times the interval. Because we're using 2 discrete intervals, so 2 times dx. And then the range, we also need to be careful because the 2 endpoints, the beginning and the end, are truncated. So we start at 1 and ending at the length minus 1. And we can copy this to see what is the central difference. So y of central is here. Okay, so we have calculated these differences, the velocity, and we want to plot the velocity in a 1 times 4 grid. So you can copy the code from last time, but I'm gonna code from scratch. So subplots, column, so 1 row, 4 columns, and different axes. Okay, like this. And then for axes, number 0. So the first axis, I want to plot the t and velocity. Okay, I should name them velocity instead of y. So velocity, backward, and then velocity central. So velocity forward is plotted in 0. Okay. Now gives me an error that x and y does not have the same shape. Again, it's because in those numerical method, we are truncating points. So the derivative have 30 points, but then t, we have 31 points. So we need to do some list splicing here. So for forward method, we're losing the last point. So indexing to the -1 point. Okay. And then similarly, we can copy that. For the first plot, we're plotting, the second plot, we're plotting the backward difference. And then for backward difference, we're discarding the first point. So starting from 1. Okay. And then similarly, we can do for the third plot, we have central difference. For central difference, we're discarding the first point and the last point. So splicing like that. Okay. And then the last one, we plot everything. So let's label them first. Label them as backward, forward, backward, and central. Okay, and then I copy all of these because all the plot are the same, but I'm just plotting it at the 4th plot with index 3. Okay, so now it appears at the 4th plot. And let's make some adjustment so that it looks nice. So for I in range 4, this means that I'm applying this to all the plots. So axis of I, let's say set x label as t, set y label as velocity, which is v of t, and what are the units? Centimeters per second, and then t is second. Okay, and then for multiple subplots, we can use plt.tight layout to make them uncluttered. And this looks like very tall, so we can adjust the figure size. So fig size is equal to, let's say, 20 times 4 or 5. Too small. 10 times 2.5, okay, like that. So we can make adjustments accordingly. And then we can put the legend down as legend. Okay. So some important things, actually, I want to discuss that if we only look at the forward and backward difference, on the last plot, they all look the same, right? It's just shifted by 1 frame. If you think about it, it's reasonable because all the calculations are the same. It's just how we assign the t is different. So the backward difference is assigning to the later point, and the forward difference is assigning to the earlier point. But the central difference is a little different. The central difference, if you look at the green point, has less variation compared to forward and backward differences. As you will see later, it's because it has smaller errors. So if we go through the participation survey, how many data points did backward difference lose? It should be we lose 1 point, and that 1 point is the beginning point. Okay. And for central difference, we are losing 2 points, and the 2 points are the beginning and the ending points. I think we also have a forward difference one. So for the forward difference, we also lose 1 point, and that 1 point is the ending point. Okay, any questions? So this is an ideal scenario that we have data from sampling the same sampling interval. So the sampling interval is constant, but sometimes the sampling interval is not constant either. So what we do? We can just use the formula for the slope since we're just approximating it using the slope of the secant line. So you can try out the forward difference method. So we have defined t and position, and the forward difference method is just the same thing, but instead of the dx, we put x I plus 1 minus x of I. And then you can do the same thing for backward and central difference. Any questions? Okay.
It'll be like.
Oh, dude, it's what we did last week. It's just, if provided we can complete it, and turn it in. It's whatever we worked on. Yeah, that's what we gotta turn in by tomorrow. I think it's just to make it in.
Oh, you did.
Yeah, we need to get these. I feel like to the end of this. It wasn't. There's 6 practice problems on that, and then there's some guided ones, but I think the main thing is the 6 practice problems. There's a lot of copying and pasting.
Like, or do you like copy and paste?
It's pretty,
How do you, so how do you go access?
yeah, so. Let's say,
Sorry.
no, you're good, you're good. Look at.
Like,
I just, so it'll give us. The practice problems are already filled in.
yeah.
And so you can copy the code from the practice problem, and then you just replace it with the functions and the limits of the graph that they provided in the actual problem that we're supposed to do, and then you just generate it. It's pretty, I think the guided questions and the practice problems, I'd say, are pretty consistent.
No, that's what I was saying. No, I wouldn't, that's what.
Yeah.
Is this problem?
Yeah.
Like, you just want to.
So there's 2 different ways you can do it. If you go to B courses, like, so you can get it into oh God, what's that? So you can get it into grid scope is what you're asking? Okay, so there's two different ways you can do it. If you go to the B courses, there's an announcement, and he gave us a code that we can generate, we can run it. So I had issues with it last week. So the other option is you can just hit Control P and get it into a PDF. Yeah, Control P and get it into a PDF and turn the PDF in that way. I will say, if you do it that way, you gotta add a ton of code at the end of it, just random blank codes, because otherwise it'll cut out like half the assignment.
We need to be more like sort of. We should be more like. But it does.
We need to run.
People getting down to, because it takes 2 positional arguments that Taylor gives. Oh my God.
Yeah.
Small one. Right, that's about it. It's even-
This is.
Basically just copy and paste, but the hard part is where to change.
Yeah. Okay, so. With that. When you did what that.
I agree. I can't understand.
It's because of, so this central difference.
It's just, too slow.
Yeah, I think
You
it's
would
would
stop.
Yeah.
It's just.
The -16 to -17 just.
That's what explained this first day, right?
Yeah.
But it's just.
That's correct. But volume.
Yeah, there we go.
It's difficult because
It looks like you do actually have to change. The. I think you should leave the time as it is. Change the.
you can say your words.
Like how you mentioned.
Right, but then-
And you use restart the last page.
What was the length of? Like the. So what was the issue? Are you starting at 0? Then it changes that, like. We're actually calculating.
The second one.
And here. Recognize your standards. Lots of lines. Legends who are figuring out.
A lot of the rest of them kind of did it, man.
So.
Maybe 1 year. But if I wanted to.
It's. Yeah. Value.
Good one. I don't know, my problem. So.
Similar.
Oh.
It was there for.
It was there for. What's your for one? You don't know. But.
This is. Here, value.
Oh, wait. Maybe this is to do with the way you're calculating the number of points in all of these, because if you're inputting this, yeah, like I see what you're doing.
Because all of here is correct.
Yeah. Sorry, you're, sorry, I think you're looking at 10.4.
That's it.
That one, so maybe you should be doing. Maybe you should be doing that on something. Because you have to, only calculate up to T minus 1.
That's what I had initially, like, I didn't.
So like you tried that one here.
I basically remember the first and the last T down and then wait, something. And so do that.
It's because we're supposed to have 17,
So like this, for example,
and you only have 4,
this work for you?
right? It says 10 to the negative 17.
You should do here. What's negative 17?
Yeah. Oh, I have for negative 8.
This to me makes more sense. Maybe we should verify.
So we could
I wasn't seeing like what looked at, but like what he was mentioning earlier, right? Like you get rid of.
Yeah, no, I
Yeah.
get that, just like don't understand where the specific error is. But like I said, it's the T is too big.
Of course, we're
Yeah,
also
these are different sizes.
Basically, but that's wrong, I'm small.
I have a question about standard deviation.
So to do that, you can change the mean to STD.
Interesting, okay.
So you can copy and paste.
Did you see where it was?
Any perspective
Specifically.
to that? And then I noticed you were able to run, 3 lines of code at any given time. How do you?
So that's for.
This is
I'm
the
not sure if this
fourth
works in code.
Okay. So then I do.
Just tell me
I
when.
can show you.
Oh,
how
here we
to
go.
do it. Here we go.
Yeah, so he's doing it
Okay,
from
he's
the
doing
time
the
as
T.
well.
Oh, okay.
Yeah, because like, yeah. Like normally you don't have to screw it here.
Yeah, there we go. It's graded on completeness, not on.
That is true. What steps are you taking?
Problems.
Okay. Much.
Yeah.
One problem 8.
Well, yeah, but we didn't see.
Oh,
E
yeah, we
or
still
E.
haven't even finished C, D. Oh my god, I forgot about those.
Okay, I'll make it shorter. I'll make an announcement to cut it off.
You could have got that problem.
I'll put the error part next time.
Yeah, so we barely did, we
We
barely did
barely-
A, B, we still have C,
We
B,
have C,
E.
D, E.
CDE are conceptual.
That's conceptual.
Oh, okay.
So that's 8, 9, 10.
We could have done all of this.
I'll cut it at the error part.
The air part, which is the air part?
Cause I didn't cover,
This is there.
yeah, didn't do the class.
So.
So I think
wait, it's not that.
To define.
This part,
You're trying to plot the.
so not.
So absolute error.
So. Not. Or increment.
I'm not sure why that thing. But I think
So
it's
do
not
this.
define it as a function.
Don't,
When you define functions.
Don't do problem eight.
okay, don't
Okay.
do problem 8, 9.
Thing, you know what I'm talking about?
Just do problem 7.
Just do problem, so just finish problem 7.
Okay, we'll make it to the next one, so we're gonna get it done.
Oh,
So we don't
Oh.
lose any-
that's good.
Yeah, but.
So this will just be on the next slide. That's true.
Okay.
This part?
Yeah. Yeah.
It's too much, it's my problem.
Yeah, that might be the reason why.
Okay, so
Okay, so from
From
here
here,
is
it's just like.
from there, don't.
don't do it.
Just finish 7.
Right, even this, I think it's an absolute. So. From here down
Ah,
below,
damn.
because I didn't cover it.
That is-
Okay, so only this one. I just have to put in my life.
So, yeah.
So problem 6.
Also, is it okay if my problem 6 was on 103?
Yeah, because mine's from 0 to 4.
Let me see if it's, all right.
We're almost done. We're almost done.
It is not.
No, awesome.
Actually, it needs to be-
Why was that?
Yeah, we can touch your life.
Yeah.
Much confidence. Everyone's copy and pasting.
I gotta brush up on Python.
This is-
Oh.
All right.
That's good to know.